So I welcome you all in this course of Introduction to Heat Transfer, a practical oriented approach. I am Amraraj Sawant from Department of Mechanical Engineering. So today is a lecture number 6, Thermal Resistance and Conductivity. So before this we have gone through certain concepts of heat transfer, what are modes of heat transfer, how the three-dimensional heat conduction equation is there, and how we derive or how we simplify this three-dimensional equation to one-dimensional equation, and what is the convenience or what is the relevance of Fourier law in the heat conduction. So right now we are going to see how the thermal resistance or the thermal conductivity, which is a property of material, is influencing the heat transfer in the mode of conduction. So heat transfer is a vital in engineering, as we have discussed before in many lectures. So key terms in this heat transfer is the thermal conductivity and thermal resistance, and both are the important material properties that are very much influencing the heat transfer in materials. So if you can consider a three-dimensional heat transfer or two-dimensional heat transfer or one-dimensional heat transfer, whatever may be the type of heat transfer, steady state or transient, the main function or the main factor or the main property of the heat transfer is a thermal conductivity, which is denoted as a K, and the thermal resistance, which is denoted as a RT or RTH, is a thermal resistance. So these properties are mainly influences the heat transfer and how much heat transfer will going to take place. Okay, so we are going to see in details in further slides. So what is thermal conductivity? It is a material property indicating how well it conducts the heat. So what it means to see here is that, so how fast or how quickly or how slowly the material is going to conduct the heat, or the material is transfer the heat from one side to another side of that material. The material property which tells us about how fast or how slow the heat is going to transfer, the material property is called as thermal conductivity. So it is denoted as a K, and its unit is watt per meter Kelvin. So if that thermal conductivity is high, okay, so I will denote this as directly as a K rather than writing a complete thermal conductivity. So high thermal conductivity means high heat transfer or faster heat transfer, so quickly heat will be transferred, and low thermal conductivity means slowly heat will be transferred, or the resistance to the heat transfer. So we have seen in Fourier law for conduction or a steady state. Steady state means what? The temperature will not going to change with respect to the time. So the Fourier law states that Q is equal to minus K into A dt by dx, where dt by dx is a temperature gradient, A is a surface area where the heat transfer takes place, and K is a material property. As I have said before, the K is a thermal conductivity, which is a material property which tells us about how fast or how slow the heat is going to transfer from one side to the another side. So this equation, if we simplify as a minus Ka dt by dx is a total distance traveled by the heat. So we can consider it is as a L. Okay, so if we rearrange this term mathematically, just mathematically interchanging this term, we can find out how much or what is the value of K. So interchanging these terms mathematically, so K is equal to Q into L. See, this L is going this side, and so therefore K, which is thermal conductivity, is equal to Q into L divided by A into delta T. Delta T is a temperature difference. Okay, before in the first lecture I have said that the heat transfer will only occur when there is a temperature difference. If there is no temperature difference, that means there is a thermal equilibrium, then no heat transfer will take place. So this is also important term in heat transfer. So here we can find out what is the value of K, okay, where Q is heat in watt, so A is area, and dt by dx is a temperature gradient, as I have said earlier. So what is the physical meaning of conductivity? So as I have said, the high conductivity means how fast, high conductivity means fastly the heat will be transferred from that material, okay, and low conductivity means the restriction to the flow of heat transfer, or the heat transfer will going to transfer slowly, okay. So it determines the rate of the temperature equalization, means it determines the rate where the temperature or the heat transfer will takes place, how it takes place, fast or slow. So let's consider again this as a metal rod. If this is a metal rod, okay, then if I am going to put the one side in a burner, then the heat will going to transfer from one side to another side, okay. But if it is a let's say wood, okay, or some refractive material, okay, which is having a low conductivity, then if I put this side in a on a burner, then this side will take some time, okay, or this side will not be getting heated, because this the material property which tells us about how the heat is going to flow, fast or slow. That material property is called as a thermal conductivity. So what is mean by thermal resistance? So thermal conductivity, as I have seen earlier, so thermal resistance is actually a reciprocal or vice versa property as a thermal conductivity. So resistance, as the name suggests, the thermal resistance is to heat flow in the material or a system, means the thermal resistance is a resistance in a material to flow the heat. It will put a restriction, or it will put a barrier not to conduct heat from one side to another, okay. There is a need for this also in everyday life or in engineering application. We have certain examples that we need a heat transfer, but there are certain examples like in a building insulation, or in your home, if there is some air conditioning, then that air conditioning outlet or duct system has an insulation. So for insulation, why we provide insulation? Not to conduct heat. By not to conduct heat, we will have efficient air conditioning system. So in everyday life, we have certain examples like where we want heat transfer to be takes place, and where we don't want to heat transfer to be takes place. So the thermal resistance is a property where the heat to be transferred, which will have some resistance or some barrier, okay, and it depends on the material and its geometry. Similarly, just before I have said that the Fourier law, so in same Fourier law, by rearranging the term, we can get the resistance resistance term mathematically. So here same Fourier law, Q is equal to minus Ka del T divided by del X, where del X we are putting it in a length term, and if this term we will put here beside this below this L, then delta this equation will become delta T divided by L divided by K into A, and this term L divided by Ka in a conduction is called as a resistance in a conduction. Once again I will say that this term L divided by Ka is equal to resistance or thermal resistance in a conduction only. For convection and radiation, this resistance will be changed, okay. We are here considering only conduction mode of heat transfer. So this resistance L divided by Ka is where the conduction happens, okay. So RTH, finally we will get RTH, where RTH is a resistance is equal to L divided by K into A. So here you can see directly that K is a thermal conductivity, as we have seen in previous slides. So RTH and K are reciprocal to each other. So where the thermal conductivity will be higher, okay, where the thermal conductivity will be higher, the RTH, the resistance will be lower. Or similarly, where the thermal resistance will be higher, thermal conductivity will be lower, vice versa. Okay, so units of thermal resistance is Kelvin per watt. Okay, so conductivity versus resistance, just I have explained here. The thermal conductivity and resistance are reciprocal to each other. Similarly, here just stated in word form. So inversely relation. So high thermal conductivity, that means low resistance, okay, or low thermal conductivity means high resistance, and this is used for as a metals, and this term, that is low conductivity and high resistance, which is used as a insulators. And what is their applications in your engineering or day-to-day life? You can see that your electricity connections in your home, which is made up of metal wires like a copper. Before 1980 we use aluminium. Okay, so for conducting the electricity or heat, okay, we use the metals. Why? Because it contains, or they contains, high thermal conductivity. Easily they conduct electricity or heat. But for insulators, like your right now you are using, if any applications, any electrical appliances, so then that appliances will have the rubber wire or some polymer material which is used as an insulator. So that insulator will have lower conductivity and higher resistance, so that the heat will not be propagated or heat will not be transferred from one side to another. Okay, so useful for comparing the materials in heat transfer. So what is mean to say here? So where the need of material, where the need of insulator is there, then we can use lower conductivity material, and where the metals or where high conductivity is needed, where the high heat transfer is needed, then we use high conductivity material which is having low resistance. Similarly, when insulator, or when our heat transfer, we don't need heat transfer to be taken place, then we use insulator. For that, the low conductivity material which is having high resistance, we can use that material. So real life applications, like in electronic cooling. Okay, so electronic coolings, you are using some PCs or laptops. So thermal paste or heat sink ensures the heat flow away from the component. So thermal paste and heat sink are the material used to propagate the heat easily. So they are high conductivity material. So just keep in mind that first, where the high thermal conductivity is there, the heat is going to flow easily, and where the heat is going to flow easily, we are going to use high thermal conductivity material. Second is, where the heat is going to be restricted, there we used as an insulator, where the heat is not going to flow easily. So that material conductivity K is lower, where high conductivity material K is higher. Simple is that. Okay, so use the material with a high thermal conductivity. Why? Because we have to cool that part, electronic part. So that's why the thermal paste or heat sink are used. Okay, in building insulation, here in building insulation, we don't require heat to be transferred from outside or inside. Okay, so here we have to use insulating material. So insulating material properties are what? Thermal conductivity will be lower and resistance will be more. Simple is that. So walls and roofing uses high resistance material, which is R value is higher and its K value will be lower. So that type of material we have to use in building insulation. Okay. Similarly, this is a real life example. In a winter, you are using winter clothes. Okay. In winter, not to transfer the heat from atmosphere or surrounding to your body, you are using woolen or woolen clothes. Why it is so? So the woolen has a property that they will not transfer the heat easily. They will not transfer the heat easily. I am not going to say that they will not transfer heat. They are not, the woolen has a property, or some insulators has a property, that they will not transfer the heat easily. They will restrict the heat. So that's why we use woolen material cloths in a winter. So using this low value, low K means thermal conductivity materials like woolen and fleece, that traps the air. Okay. And similarly, the lower K means lower thermal conductivity, means higher resistance. Likewise, I just said that this, by this formula we can say that the resistance and the thermal conductivity are the reciprocal to each other. When the thermal conductivity will be more, the resistance will be lower. Okay, for same material. So these principle we are using in a real life example. So cooking vessel, we need heat to be transferred easily to cook our food. Okay. So copper and aluminum of high conductivity for fast heating or fast cooking is used. Okay. So stainless steel or ceramic of low thermal conductivity for safety and insulation. You can see that you are using some pan or some cooking vessels. The one part which is placed on the burner is made up of metal, but the handle is made up of ceramic. Why it is so? Because the handle, where the handle is placed, we don't need the heat to be transferred, otherwise you will burn your hand. Okay. So that is why the low conductivity material is placed on the handle of your cooking vessel. Okay. So car radiator and engines where the high thermal conductivity material are used for cooling, and as a design consideration, resistance to maintain the engine temperature, means high thermal conductivity material were used where we want the heat transfer to be takes place at a faster rate to cool down the engine. Otherwise the metal part will have some problem due to the high heating. Okay. So this is the general life or general table for thermal conductivity. Copper, the thermal conductivity I just stated before, it's having unit watt per meter Kelvin. The copper having thermal conductivity 385, aluminum having thermal conductivity 205, steel having thermal conductivity 50, concrete which is used in a building construction which is having thermal conductivity 1.1, water is having thermal conductivity 0.6, wood having thermal conductivity 0.12, glass wool which is used as an insulator in a refrigerator, so it is having thermal conductivity 0.04, and air which is having thermal conductivity 0.025. So from this table you can see, or you can understand, that high conductivity material we are using for easiness of heat transfer. Okay. And low conductivity material, these are low conductivity material we are using where we don't want the heat to be transferred. Okay. Simple is that. So factors affecting conductivity is a temperature. First is a temperature, second is a moisture content. As you can see that here water having thermal conductivity lower, so it acts as a thermal resistance to the heat transfer. So if moisture or water vapors are trapped, okay, then the heat transfer will be less. Okay. Porosity, it is a material property where the air is trapped in pores, and as you can see here, air is also having low thermal conductivity, so air will also resist the flow of heat. So material structure, how the material is designed according to the shape and the design. Okay. Impurities, also the impurities let's say some impurities having high thermal conductivity but some impurities having low thermal conductivity. According to that, our designed or application based engineering or any applications, we have to take a consideration of these impurities and their thermal conductivity or resistance property. So summary, the thermal conductivity basically is a ease of heat flow, how easily the heat will flow, and thermal resistance is opposition to the heat flow, how to restrict the heat flow is a thermal resistance. We can use this term RTH is equal to L divided by Ka to design thermal system in only conduction heat transfer. For convection and radiation, this resistance term will be different, okay, that we will see in next slides or next lecture. So thank you very much. So I conclude this lecture. You will have 20 multiple choice question assignment on this lecture, and the lecture notes in PDF form will be available to you in discussion forum. So please feel free to ask me anything about this lecture and this course in the discussion forum. So also I bring your attention that while attempting your assignment, you will get to know your score at that time. Okay, so thank you very much.